Okay, and for what we have in this set of problems, okay, we have in the case of dy over dx plus 2xy squared is equal to 0, okay, we can separate the variables, okay, and first of all, okay, we can separate the derivative dy over dx apart from the variable term. Okay, so if we isolate, so taking 2xy squared away from both sides, okay, so we have dy over dx is equal to negative 2x y squared. Now in terms of separating the variables, okay, so we can simultaneously divide by y squared and multiply by dx. So here we're going to have dy over y squared equals negative 2x dx. And upon separating, we can integrate. And again, for the integral of dy over y squared, you can see we have y to the negative 2 dy. And the antiderivative, okay, you will have the negative of the multiplicative inverse of y, followed by the constant, and say we have negative 1 over y. Okay. And so we have, upon integrating, so we have negative 1 over y is equal to, and for the integral of negative 2x dx, we have negative x squared followed by the constant, and we can go ahead and change the signs. Okay, so we have 1 over y is equal to positive x squared, and I would just leave the constant in terms of addition. So just, you can either say plus c, but I'm just going to choose a different letter. We'll just go with the letter A. And taking the multiplicative inverse, okay, so taking the reciprocal of both sides, so we have y is going to be equal to 1 all over x squared plus the constant. And that will be the general solution of what we have for this particular problem. Okay, now for what we have in the next item, which we have as another separable differential equation, so we have dy over dx is equal to y times the sine of x and if I separate the variables, okay, so I can divide by y and multiply by dx. So we have dy over y is equal to the sine of x dx, and integrating, okay, so we have dy over y, and I know that my notes have had like the natural logarithm of the absolute value of y, but I'm just going to go ahead and write this as the natural logarithm of y is equal to the negative of the cosine of x followed by the constant, and taking care of the natural logarithmic notation. So we can say we have e to the natural logarithm of y is equal to e to the negative cosine of x plus c, and I can just expand upon this. Okay, so we have e to the negative cosine of x times e to the c, and again we have, in the case of e to the c, we can write as a constant raised to a constant resulting as a constant. So working with what we have now, e to the natural logarithm of y, okay, that will go to y, and we have is equal to a, and you can use the letter c, but we got a constant In this case, I'll say a, and we have times e to the negative of the cosine of x. And that would be the general solution for that problem. Now for what we have in the case of the next item, okay, now we can separate once again, and in this equation we now have the quantity of 1 plus x times the derivative dy over dx is equal to 4y and looking at separating the variables. Okay, so I can say I have dy over y is equal to 4 over 1 plus x, and integrating. Okay, so we've got dy over y once again, and again technically it's the natural logarithm of the absolute value of y, but you can write this as the natural logarithm of y. And for 4 over 1 plus x, okay, you have, say, 4 times the natural logarithm of the absolute value of 1 plus x. I'm going to write this as the quantity of 1 plus x. And we have followed by the constant. And to clean things up, okay, now the coefficient 4 can be written as an exponent. So just as a refresher, okay, so you have like if you have a logarithmic term, so you have a times the natural logarithm of b, we have the natural logarithm of b taken to the a power. So this is going back to pre-calculus where you have alternating between leading coefficients and exponents. So we have the natural logarithm of y is equal to the natural logarithm of the quantity of 1 plus x raised to the 4th plus c. And again, taking care of the natural logarithmic notation, we can treat both sides as powers to which e can be raised. And again, just by then, for what we have on the right hand side, okay, you're going to have e to the natural logarithm of the quantity of 1 plus x to the 4th. We have times e to the c, and a constant raised to a constant we have at a. So we have on the left e to the natural logarithm of y. Okay, this will go to y. And from e to the c I have a e to the natural logarithm of the quantity of 1 plus x, all raised to the 4th power. So we have y is equal to a times the 4th order of the quantity of 1 plus x. Now, for what we have in the next set, okay, a little different layout and in the set. So we got 2y dy over dx is equal to x all over the square root of x squared minus 16. And in this problem, okay, we have an introduced initial condition whereupon we have whenever x is equal to 5, we have that y is equal to 2. And if we look at separating the variables, so what I can do is multiply by dx So we have 2y dy is equal to x over the square root of x squared minus 16 dx, and integrating on both sides. Okay, so for 2y dy, okay, so this will become y squared. Now for what I would have over to the right, okay, so just sidestepping a bit, for x over the square root of x squared minus 16 dx, here I can utilize u substitution. So if I set u equal to x squared minus 16 and taking the differential, okay, so u goes to du, x squared minus 16 goes to 2x dx. And putting dx in terms of du, so we have the dx is equal to du over 2x, and if I were to substitute accordingly, so we have the integral, so we have x over the square root of u, and again I have, in lieu of dx, I have du over 2x, and if you notice, we're going to have the x's to cancel out, so you're going to have 1/2 of the integral, and the reciprocal of the square root of u du, we can write this as u to the negative 1/2 du. And with the power property of integration, so we got 1/2. Then we have times what's going to be 2 times u to the 1/2 plus c. 1/2 of 2 is 1. U to the 1/2. And despite then, you can just write this as a radical, whereupon we have the square root of u plus c. And with the back substitution, okay, we're going to end up at the square root of x squared minus 16 followed by the constant. Okay, so for what we have here, we have y squared is equal to the square root of x squared minus 16 followed by the constant. And for what we have now, we have y of 5 is equal to 2. Now I could go even further and simplify, okay, what I have in terms of y for first order. Okay, but just for right now, I'm just going to leave this, okay, as a square. Okay, so we got y of 5 is equal to 2. Okay, so y is at 2 whenever x is at 5. So filling again, so we have y to the second becomes 2 squared. And the square root of x squared minus 16, we have 5 squared minus 16. Within the radical, we have plus a constant, and we have 2 squared is 4. 5 squared is 25 minus 16 is going to be the square root of 9. And plus c. So we had that 4 is equal to 3 plus c, and it's going to follow that the value of the constant will be 1. Okay, and so for what we are going to have in this particular case, right, so we're going to have that y squared is going to be equal to the square root of x squared minus 16 followed by the addition of 1. And as far as I'm concerned, that would suffice as a complete answer. Okay, but if you were to write this in any other fashion, say if you were to put in terms of y, and I think the author has the result in terms of y squared, but if I had to do this like in terms of the variable y in first order, okay, you would just consider the square root property of equality, where you would have, in this case, you would have like y is equal to plus or minus the square root of the square root of x squared minus 16 followed by the addition of 1. Okay. But again, just for what we have in y squared, okay, that will suffice. But if you had to itemize y and write it in first order terms, again, you would be considering the square root property of equality. Also in the mix, okay, just going back to what we have with the natural logarithmic exponential base e. Say we have dy over dx is equal to y times e to the x. Okay, so you have a separable differential equation. And simultaneously dividing by y and multiplying by dx. So you have dy over y is equal to e to the x dx, and integrating again for dy over y, again just leaving out the absolute value notation, so you have the natural logarithm of y is equal to, and for the integral of e to the x dx, okay, so that's going to be e to the x plus the constant, and expressing in terms of y equals, okay, so I can take e to the natural logarithm of y is going to be equal to e raised to the e to the x plus c. So you have e to the e to the x times e to the c and just write this as a so you have a times e raised to the e to the x. So for what we have here, e to the natural logarithm of y goes to y, and that is equal to a times e raised to the e times x, or make that y is equal to a times e raised to the e to the x degree. And if this were written in any other fashion, you can also write and say we have a, and like the author would have the notation like exp e to the x, where you have signifying that e to the x is the power to which the exponential base e is raised. Now, I did not mention this, but there is an initial condition where we have whenever x is 0, we have that y is equal to 2e so looking at solving for y specifically, where when x is 0, we have that y is equal to 2e. So filling in, so we have 2e is equal to a times e raised to the e to the 0. And guess what? So we have 2e is going to be equal to a times e, and guess what? E to the 0 is just going to be 1, and guess what? We're going to have e's to cancel out, and so we're going to have that a is equal to 2, And so for the specific solution, okay, we had that y is equal to 2 times e raised to the e to the x power. You can write it in that fashion, or say that we have 2 times the exponential in e of e raised to the x. And in this one case, you have a reminder, okay, of working with exponents. We have blending together the natural logarithmic base e and how we're going to have the exponential properties, especially from pre-calculus and to some extent from calculus, to all intertwine. Okay, now for 27 we have dy over dx is equal to 6 times e raised to the 2x minus y degree. And for the initial condition laid out, so we have that y naught is equal to 0, and I can set things up along the lines of separating the variables. But I'll tell you what, just for right now, let's say for what we have on the right, if we sort of separate what we have in the variable degrees, okay, so you got 6 times e to the positive 2x minus y, and think of this like e to the 2x minus y when we say have 6 times e to the 2x. And for the e to the negative y part, we can say that that is going to be the multiplicative inverse of e to the y. And if we look at separating the variables, I can simultaneously multiply both sides of the equation by e to the y and also by dx. And in the setup, I can go ahead and integrate left hand side. Okay, we have e to the y, and for 6 times e to the 2x dx, again, chances are you already see the result, but I know in the case of the exponential base e to powers, it is oftentimes easy to get the performance of taking the derivative and the antiderivative mixed up. So just taking the differential, so du is equal to 2 dx, and du over 2 is equal to dx. So we have the integral of 6 times e to the u and dx. Okay, so you have 1/2 of du and so we're going to have the integral of 3 times e to the u du, and following through, so we're going to have 3 times e to the u followed by the constant, and back substituting, so you have 3 times e to the 2x followed by the constant. Okay, so just putting back, okay, it does get a little bit long-winded, but just as a reminder, so when you're taking the antiderivative of e to the 2x, you're taking 1/2 of the coefficient, whereas if I took the derivative, I'll be doubling. And now, so we got e to the y, and so for what I can do now to go from e to the y to y itself, I can just take the natural logarithm of both sides natural logarithm of e to the y. Okay, that will go to y. And we have is equal to the natural logarithm of 3 times e to the 2x, followed by the constant, and specifying what the constant will be so as to attain y at 0 whenever x is at 0. So y is at 0. We have is equal to the natural logarithm. Okay, and we got e to what's going to be the 0. E to the 0 is 1, so you have the natural logarithm of the quantity of 3 plus c. And if I were to follow through, I can take care of the natural logarithm on the right if I treat both ends as powers, to which e is going to be raised. So e to the 0 is going to be 1. 1 is equal to 3 plus c. And we have that c is equal to negative 2. So if I go back to the general solution, we have that which will ensure that y at 0 is equal to 0. We end up with the natural logarithm of the quantity of 3 times e raised to the 2x, followed by the subtraction of 2.